Okay, so I'm going to solve some practice problems from chapter 6, which is Sn1, Sn2. I think we don't do eliminations in this one yet, so just be Sn1, Sn2. So identify and label the nucleophile, substrate, product, solvent, and leaving group. So in an Sn1 or Sn2 reaction, you always have the nucleophile, and that's the thing that's going to be doing the attacking. And you can easily identify this by seeing the starting material and the final product. So if this starts with bromine, and the bromine is swapped out for this whatever, then you know that that's going to be the thing attacking. So whatever is swapped out here, that is the nucleophile in a substitution reaction. So that makes it easier to identify. It's what's substituting in. The leaving group is what has substituted out. So this is the leaving group before it's left. This is after it's left. I'll accept either of those as the right answer. So the leaving group gets substituted out for whatever the nucleophile is in a substitution reaction. Usually, if it's negative like this, it's an Sn2, but we can talk about that more. Overall, the substrate is what is holding the leaving group. So what's being acted upon by the nucleophile is the substrate. And then the solvent exists basically so that these molecules can interact with each other to undergo this reaction. So if there's something that you don't see how directly it plays a part in the reaction, but it's still present, oftentimes drawn around the arrows, but not always, that is a solvent. So that is the nucleophile, the substrate, the products. Oh, the products are what's on the right side of the arrow usually. Always. I don't know why I said usually. And the products in a substitution reaction are going to be the substituted substrate. So the leaving group is left, and the nucleophile has attacked, and then the leaving group after it's left. Sometimes you'll also see this as ONA, and that's because there's a positive sodium or even OK plus or something like that. That's a positive counter ion, and so you can also write it present here, but because it's just a spectator ion and it's not playing an active part in the reaction, oftentimes that's left out. Okay, so we have Sn2 or Sn1 based only on the substrate. So which would these substrates be most likely to undergo? And what's nice about this is if you just know that it's primary or tertiary, you can take a good guess. So in this case, this is primary. This one's tertiary. A primary substrate is going to favor Sn2. And the reason for that is the Sn2 reaction is a nucleophile is going to come in and attack. Whatever nucleophile you have will come in and attack as the leaving group leaves. So it needs to not be super hindered or very bulky around this carbon right here, or else there's not going to be room for the nucleophile to come in. So if it's attached just to one carbon, it's going to be much more likely to favor Sn2 because the nucleophile has plenty of room to attack. So that would be my explanation. Primary substrate for leaving group favors Sn2 because it doesn't have steric hindrance. So steric hindrance is the fancy word for stuff is getting in the way of this nucleophile coming in and attacking. But this is tertiary, so it has a ton of stuff that's getting in the way of something coming in and attacking. So actually, this would be more favorable to have the leaving group leave in a carbocation form. So in this case, it would favor Sn1, and that's because the tertiary substrate can stabilize the carbocation after the leaving group has left. And also, I want to note when I say tertiary substrate, I mean specifically it's tertiary where the leaving group is, not if there's any tertiary carbon or any primary carbon. It's right where the leaving group's attached. Okay, for the given Sn2 reaction, draw the product of the reaction and show the stereochemistry. So in an Sn2, this has that spectator ion like I was talking about. So CH3O minus is what I draw. If I ever see that, I just basically get rid of that spectator ion. I don't pay attention to it anymore. This is going to come in and attack, and a key feature of Sn2 reactions is that they do what's called a backside attack. So this is actually going to attack kind of from the top, and the hydrogen will be pushed around. So it's called inversion of stereochemistry. So actually, right there where the reaction happened, this OCH3 is going to take in at the axial position, while this hydrogen has been pushed to the equatorial position. The stereochemistry there inverted. We also have the Br minus at left. And over here on this carbon, nothing has happened. So this stereochemistry on this carbon doesn't change. We only see a change in stereochemistry right at the site of the reaction. This is a solvent. It doesn't really play a part. If you want to, you can also put Na+ there. So these are the products of the reactions in the mechanism with a proper stereochemistry shown. Okay, this is the second part of question 3. So we're actually going to have, it's the same nucleophile. It'll come in an attack and kick out this tosyl group. Whenever you see OTS or OMS, that's a tosyl or a mesyl. So it should look like this, or I think it's just 2 oxygens. A benzene ring here with a methyl group on the far side. These are really good at stabilizing. So if they're attached like this, they're good at stabilizing themselves, so they are good leaving groups. So at first, whenever I was doing this and I didn't recognize the tosyl, I would, there's an oxygen between these, sorry. I would just cross that out and write leaving group. And then it was easier for me to see what was happening with that tosyl, but that's up to you, whatever you want to do. So the leaving group leaves, and the stereochemistry is inverted. So actually, this has attacked from the backside. So OCH3 attacked from the backside, and the hydrogen has been pushed to the front. And then we have our CH2, CH3, and our methyl. Neither of those have changed. So we see inversion of stereochemistry. This is your mechanism, and this is your final product. Okay. Draw the mechanism and the transition state for the given Sn2 reaction in the boxes provided. So this Cn minus, I didn't mean to draw that in. I said it and then wrote it also. It's going to come in and attack, and your leaving group is going to leave. So that's the proper arrows for this mechanism. And the transition state looks something like this Cn is coming into attack as the iodine is leaving. So this maintains the electron density at this carbon without overfilling its orbitals. And I always put it in brackets to indicate that it's a transition state. So this is what the transition state would look like. And we didn't actually ask for this, but the product of this reaction, it's already given. There you go. That's why we didn't ask for it. Okay. Now for the bonus point, consider the Sn1 reaction. Assuming no other changes, what effect on the rate would result simultaneously from doubling the concentration of the substrate in the nucleophile? Well, the mechanism of an Sn1 reaction is that the leaving group leaves, and you get a carbocation, and then the nucleophile attacks, and you get your final substitution. And you get that at a 50-50 racemic mixture of both stereochemistries if it's a stereocenter. In this case, the rate is only dependent on that first step, the substrate, when the leaving group leaves and the carbocation is formed. That's the rate determining step. So if we double both the nucleophile and the substrate, it won't matter. It only matters if we double the substrate. So that will double only the rate of the reaction, not quadruple. Okay, I hope that was helpful for you guys. Please feel free to reach out to me if you have any questions, and good luck studying for your exam.